Hi, welcome to lecture 35. In this lecture we're going to talk about energy in the context of Newtonian gravity. Here's our agenda. We're going to look at Newtonian gravity more closely and we'll ask, is it a conservative interaction? That's the requirement to have a potential energy. The answer is going to be yes. We'll figure out what the potential energy looks like and draw it in a diagram. We'll consider different types of states that we can have here. So-called bound and free states. And then we'll apply those ideas to a bunch of different scenarios. We look at the impact speed of something falling from a great height. So too great, so you're no longer near the surface of the planet. Maybe it's some object from space crashing down to Earth. We'll talk about the concept of escape velocity. That's if you want to leave the planet, say in a single jump, how fast would you have to jump? We'll talk about energy in the case of orbiting objects, and this little theorem we're going to derive, or a very special case of this more general theorem. It's called the virial theorem. And we'll see what that is. It's kind of a curious relationship between the potential and kinetic energy. And finally, we're going to just come back to this MGH potential energy that we know and love from that works near the surface of the planet. And we'll see how this comes from the more general potential energy that we're considering. So let's get going. So let's just recap. When I'm near a planet, right, the force of gravity can just be written as mg. And the associated potential energy is mgh, right? And it's really just the work that would get done by gravity as you move between 2 points. Now, we already talked about the relationship between the more general force of gravity and in this case here, right? So little g is essentially this combination, everything except the lowercase m, where big M would be the mass of the planet and r the radius of the planet if you're near the surface. And then, so those together are essentially to make up the little g. Because those three wouldn't change as long as you're just considering different objects in the surface of the same planet. Now the question is, what happens here? Is there a potential energy term? So to ask, is there a potential energy term, we really have to ask, is Newtonian gravity, the Newtonian gravitational force, is it conservative? Right? Remember, conservative had a fairly technical definition. Was that the work is path independent, as long as you go between 2 points. Only matters where you start and where you end, not how you traveled in between, in order to calculate the work done by that force. In practice, forces are conservative if the direction of the force doesn't depend on what path you take. Right? So if the direction and strength, I should say, of the force only depends on where you are, but not which direction you're traveling at that very moment, then the force tends to be conservative. I say tends to be because there's a sort of mathematical loophole, namely having forces that go in circles with a non-zero curl, but you shouldn't worry about it right now. We can worry about it more someday in the future, and we'll talk about vector fields and their properties more generally. So gravity does not care which way you're going, it only cares where you are. And that's kind of the sort of hand-wavy justification for it having potential energy, but you can always do a calculation more carefully by evaluating what is the work as you move between 2 points, and you can consider different paths. So the answer is yes. Right? And so we can define a potential energy. If the logic here isn't quite clear to you, maybe go back to the lecture video on work and energy, where we discuss where gravitational energy comes from. Right? So we have a potential energy term. What is it? What is that potential energy? Well, let's think about this. The force, right, is, well, the magnitude of the force is given by gmm over r squared. But the force always points in the direction of decreasing r. So here are 2 objects, right? If I start here, then this is the object, the force on which I'm considering, r would be going this way. But the force is the other way, so I'm going to put a minus sign here. Right? In practice, when we calculate the force, we know which way it points, like we know it's attractive. But because r is our variable and the force is in the direction of decreasing r, wants to pull you this way, right? There's a minus sign here if I want to be a bit more technical about it. So how do I find the potential energy? Well, here's what I know. I know that F is equal to minus du d variable, in this case dr. Right, so that whatever variable might appear in the force expression, well, here it is. Of course, in more than one dimension, it's a bit more complicated, but let's stick to everything being along a line. And that line I can just label with the r, right? All those points along this line have a single r value. In the past, I think we said du dx when we had a force that changes with x. For example, you've got a spring that you can squish or stretch, right? You might write it with an x. But it's really just a choice of what do we call our variable. Right, so this is the relationship. Again, if that is news to you, maybe you should go back to the lecture on energy diagrams and the relationship between force and potential energy. So now I can just look, I know what the force is, right? It's this, and I know it's meant to be the derivative of u being the potential energy. Remember that? That's just a funny way physicists like to label potential energy with a big U for historical reasons. And you can read up on that. You can, find out the project, find out why it's called U. Right, so this is my potential energy. So the slope of the potential energy gives me the force in the downhill direction. So let's compare. I want this, right, to be equal to this. Right, so that's how we're going to figure this out. du dr is equal to gmm over r squared. Now, how do I find u if I know that its slope, its derivative, is equal to this? Well, technically what we do is we integrate. And we can do this in an indefinite integral. But if you don't know how to integrate because you've just taken your first calculus course, you just started your path into calculus, that's okay, right? Really all we have to do is find a function u such that its derivative is this. Right now this I can actually write in a way that's kind of less confusing. Right? It's some constants times 1 over r squared. So what function differentiates to 1 over r squared? It's r to the minus 2. Maybe I should have written it like that. Like that. R to the minus 2. Well, gmm, so I need to increase the exponent by 1 because differentiating makes this the exponent one less, right? You take 1 off and multiply by whatever whatever's up here when you differentiate. So I'm going to try to find the reverse. So I guess it's going to be r to the minus 1 because that differentiates to r to the minus 2. But if I do it, I get a minus sign. So I stick a minus sign in here. In other words, I get minus gmm over r. Right, so make sure you understand this. You can always just double check. Go from here, differentiate it, and make sure you get back to there. Very straightforward. So this is going to be my expression for the potential energy of Newtonian gravity. Notice it looks sort of like the force, right? It looks gmm over r squared, except there's no square, right? It's just 1 over r. Gmm over r. Let's plot that. So here's a plot of the function. Notice the gmm is just a constant, so all the constant does is scale a function, vertically. And then it's 1 over r, so 1 over r by itself would look like this. I plot y equals 1 over x, it's going to be this sort of shape. It wants to go to infinity because 1 over 0. So you take the limit to 1 over 0, you get infinity, and it never quite reaches 0, it just gets really, really close, 1 over 1,000, 1 over a million, it keeps getting smaller and smaller and smaller. But then we've got a minus sign out front, and a minus sign makes the whole thing flip, so the gravitational potential energy is always negative. In a way that doesn't matter, right? Because we know that only gravitational, or any potential energy. Only potential energy differences ever matter. So whether this whole thing is down here or I shift it all further up ultimately is unimportant. In fact, I could add a constant over here. It would shift the function up and down. That constant would do nothing to change any of the physics, because only potential energy differences matter. And so the convention is to not have a constant here. The convention is to say, look, as r goes to infinity, this function approaches 0, meaning if I'm at the other end of the universe, my gravitational potential energy relative to that, other object at the opposite end is 0. If I'm really far away from Earth, then Earth doesn't really do anything to me regarding potential energy. That's kind of it's a very plausible convention, right? We're saying at infinity the potential energy becomes 0. But one consequence is that the potential energy is always lower than 0 if you're anywhere that's not infinity. Now over here, if you get infinitely close, right? So r is the separation between two objects. The two objects interacting gravitationally. First of all, you can't have negative r, because the separation can't be negative. You can be on the other side, but it's not the same as saying the separation is less than 0, right? How far am I away from you depends where you are, but it's definitely a positive value. But as we get infinitely close, this thing goes to minus infinity. Is that a problem? Can there be infinite energy? Well, in practice, it isn't. Because really, there comes a point, and maybe I'll draw this point right here, where if one of the objects is the planet, right? Let's always think of it as a planet, another object, it's somewhere out in space, for example. Then this might be, say, the planetary radius. Right? Some finite value of r, like the radius of the Earth. This would be the radius of the Earth. So this is r, maybe in meters or in kilometers. Well, that means really this part here doesn't really exist. So this is not accurate. In reality, because it's inside the planet. Of course, you might not have a planet. You might have two, little objects floating out in space. You and your astronaut mate. Well, but even there, you can't be, arbitrarily close. Eventually, your spacesuits are just going to bump into each other. Right? And if you were sort of overlapping in volume, then the gravitational attraction would have to be recalculated, because some of your mass would be like inside each other. It would just not work like this. So in practice, this function of cuts off here, and then something else happens. I can ask what happens inside a planet. What if I dig down? What is the gravitational potential energy if I dig a hole halfway down to the core of the Earth? Never mind that I get burned along the way in the magma. Right? Never mind that. What would it be? That's a fun little problem. In fact, it turns out that the gravitational force increases linearly as you move away from the core, and that's a problem we might well study in class. But for our purposes right here, this is kind of where it stops. Right? So only the right-hand side really exists. One exception you might come up with is a black hole. Right? A black hole is a finite mass at a point. But if you talk about black holes, then Newtonian gravity just doesn't apply anymore. We really have to analyze the situation using general relativity, right? We're no longer working in this limit where gravity behaves in a sort of Newtonian way. Newtonian gravity just breaks down long before you get close to the center of the black hole. So no matter what, there's kind of a limit here. Okay. Let's figure out some consequences of this expression and of this function, and let's do some examples. Before we do though, one more thing I did forget to say, that is, you can clearly see that the slope, right, of this graph is always positive. It's pretty steep down here, more shallow here, but it's always positive. Remember the analogy of the marble rolling down a hill. You can see wherever I put my marble, here or here or here, it's going to roll down the hill, meaning in the negative r direction it gets attracted. That matches the expectation we have given what we know about the nature of the gravitational force, that it is always attractive. Anyway, let's dive into some examples. Here's our first example. I ask, what is the change in potential energy for an astronaut traveling from the Earth's surface to twice the Earth's radius? So meaning starting at the Earth's surface and then going up in a rocket or in some such way, ending up at a distance from the center of the Earth that's twice the Earth's radius. So essentially 6,400 kilometers of radius, and then that same height again above the surface. What's the change in potential energy as we go from here to here? Well, let's work it out. The potential energy at the surface is minus g mass of the Earth, right? This is Earth, times mass of the astronaut, and it's given. Those are the two objects interacting, divided by r of the Earth. The Earth radius, 6,400 kilometers. Not squared, right? Squared is the force. Potential energy, not squared. Now, the potential energy up here, let's say at twice the Earth's radius is minus g m e times m astronaut divided by, well, the distance is 2re. So let's find the difference. Well, my change in potential energy, delta U, is going to be my final one at twice Re minus the potential energy we started with, the energy of the surface, right? So it's this minus this. Well, it's easy enough. I'm just gonna take out all the joint values and factor out all these things, and I get 1 over 2 Re minus just 1 over 1 Re. Right. This becomes minus a half, like a half minus 1, minus a half over the Earth's radius. That cancels the minus sign, and we go G M E M astronaut divided by 2 Re. Right, to check, make sure that makes sense to you. And notice there's a plus sign here, right? We have gained potential energy. Okay, that comes out from the algebra, but thank goodness it also makes sense. Alright, and now we just plug in the values, right? We could have worked out those values, numerically just by plugging in the values for the radius of the Earth, the mass of the Earth, and so on. We didn't, we worked out symbolically. Well, we're going to plug them in right now. And what do we get? Well, G, let's write down the values, is 6.67 times 10 to the minus 11. I'm going to skip the units. You know what the units are. Times the mass of the Earth, 6 times 10 to the 24 kilograms times 100 kilograms divided by, well, the radius of the Earth is 6,400 kilometers, or 6,400,000 meters. So twice that is going to be 1.28 times 10 to the 7 meters. Right, because 6.4 times 10 to 6 meters times to 1.8 times 10 to 7. Okay, well now, you could just plug it into the calculator, or you can estimate it in your head using the method I told you before, where you just calculate the powers of 10 separately, and then you just sort of, deal with the numerical values, and you're going to get, let me think, 3.6 3.125 times 10 to the 9 joules. You can double check, work it through yourself to make sure that is the answer. Okay. Really just plugging in values, finding the difference. Let's continue this example. Let's now ask, okay, suppose you're up there, you're just sitting there, you're not moving. Well, you're going to start falling back down and you're going to hit the planet. What's your impact speed? What is your impact speed as you fall from here to here? Right, in the past, you would have said MGH, this is h, right, is equal to half mv squared. MGH, the potential energy lost, equal to 1/2 mv squared, kinetic energy gained, solve for v. Well, here we can't do that, right, because there's no constant value of g. G assumes you're staying at the surface, assumes that the radius isn't changing much where you're at. So we have to work it out with this change in potential energy, right, where it comes to exactly the same thing. So let's write this down. And we're now calculating the impact speed and falling back down. And we assume we start at rest. I'm not going to write that, but I guess I am. Starting from rest. Doesn't cost me much, does it? Okay, let's work it out. We said well, if I gained that much going up, if I fall back down, I'm going to lose that much potential energy, right? So the gravitational potential energy, GPE, lost is equal to 3.125 times 10 to the 9 joules. And that better be equal to the kinetic energy gained. We're going to ignore the fact that you're going to burn up on entry in the atmosphere. Right, and then your energy is going to get, a lot of your energy gets converted to thermal energy, and it might not even make it to the ground, because you'll just be essentially completely torn apart and burned up, and you'll essentially be gas. We ignore that, we pretend there's an atmosphere, you're going to slam down on the Earth. Well, how fast? Well, let's work it out. So 1/2 mv squared, our impact speed, right, upon landing. There was no initial kinetic energy because we started from rest, and we already considered only the gravitational potential energy lost, so there's no gravitational potential energy at the end to take into account because we're working with the difference directly. Hopefully that makes sense to you. If not, pause here and make sure you understand our calculation. It's equal to 3.125 times 10 to the 9 joules. Alright, well, let's solve this. M is 100, right? We knew that, it was given. And of course, if we hadn't solved for this value before, and we would have actually cancelled out the m, by setting this equal to gm m over r. So that means we are going to have that the impact speed squared is equal to 6.25 times 10 to the 7, because 100 and a half comes over, becomes 2. 100, factor of 100 joules. Sorry, not joules, meters, we divide it by kilograms, so meters squared per second squared. Alright, let's take the square root. The impact is equal to the square root of this, 6.25 times 10 to the 7. Now I'm going to be sort of rough here. This is going to be roughly the square root of 62.5 times 10 to the 3, right? Because 10 to the 6 becomes 10 to the 3, and then there's a 10 left inside, 60.5. This is a little bit under, just under 8. 6 square root of 64 would be 8. Something like 7.9. So yes, this is exact, but that's approximately 7,900 meters per second. Again, make sure you follow the calculation, and why not pause the video right here and go back and work through it again yourself to make sure you can actually do it. Okay. Let's apply these ideas to a concept that we call escape velocity. The idea is this. Imagine you're on a planet, and suppose the planet doesn't have an atmosphere that would burn you up if you go too fast, or maybe you're on the moon, and you want to jump, or throw something, or shoot something, right? Something, you give something some initial velocity. The question is, how fast does the thing have to go when it leaves the surface so that it never falls back down? Now, in the world of MGH, and weight being just mg, being a constant, never changing, the little g, no matter how fast you go, eventually you'd fall back down. And you can think about this, like, no matter how fast I go, no matter what value for v I pick in my half mv squared for my initial kinetic energy, there is a height where all of that is going to be used up, and you're going to come to a stop and you're going to start falling back down. Right, that's the world of MGH. Of course, practice, if you go too fast, well, you're going to get really high, but then MGH no longer works, because we have to think about Newtonian gravity. You're no longer in the surface of the planet. So let's think about Newtonian gravity. Here's my graph for the potential energy, and I imagine this is the radius of the planet. So if this were Earth, I put 6,400 kilometers right here. And I don't care what happens inside the Earth right now, and this is kind of my starting value. And now I'm going to jump. And I'm going to jump, super high. As high as I can jump. So I need to have a high launch speed. And never mind that actually doing that would kill you because of the large forces on you. Never mind all that. Right? Maybe you can imagine we shoot a bullet upwards, or in some direction so it doesn't hit the planet. So initially we've got that much potential energy. Our projectile has that much potential energy. And by giving it some initial kinetic energy, we make it go, and then it'll rise up, and maybe it rises up in a straight line if we aim straight up, or maybe it rises at an angle if we shot our projectile at an angle. It doesn't matter, but we're adding some energy. So my total energy, say if I just shoot a projectile from the surface of the Earth, it would be the potential plus the kinetic, so maybe it would take me to here. It's my total energy for my first case that I'm thinking about. So in that case, this height here would be the kinetic energy added at the bottom. Right? Energy diagrams. Remember those. Again, if this doesn't make sense, go back to your energy diagrams, or that lecture, or your notes from it. Now, what happens? Well, the thing is going to go, it's going to start moving away from the planet, it's going to go up, 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 and as it does so, it gains gravitational potential energy, so it loses kinetic energy, and eventually it reaches this point. Oops. No kinetic energy left, it's all potential now, it's starting to fall back down. So that would be the highest point reached. Right, the R value here. Highest point reached on my first try. Let's call it trial 1. Okay, let's try again. Let's shoot the whole thing a little bit faster. Right, so we do it again. We start out here, that's the surface of the Earth. That's my potential energy. I can't change that being stuck on the surface of the Earth. But I can make it go faster. By making it go faster, I'm adding more kinetic energy to it. Maybe I'll add that much kinetic energy to it. This is my second attempt. Okay, what happens now? Well, the total energy is going to be up here, right? That's where the energy I start with, my potential energy. I add kinetic energy. Well, that takes me up to here. This is my total energy for my second attempt. So what's going to happen? the thing is going to rise. This is where the first trial ended, but we still have lots of kinetic energy left, right? We still have that much kinetic energy left. Keep going. But oh no, we get pretty far out, but eventually the kinetic energy, right, it becomes smaller. This is always the kinetic energy becomes smaller and smaller, nothing left. We're turning back around. If my graph is accurate, I've made it to something like 4 or 5 times the radius of the planet. It's great, you know, good job, but not quite there. But maybe I can just touch one of the geostationary satellites. Something like that. But too bad, we're going to fall back down and crash back down on the Earth. Or, you know, if I shoot at a right angle, maybe I can go around some kind of orbit. Well, depends. But I can't get away from the planet. So let's have a third attempt. A third attempt, we're going to apply a lot of initial boost. We're getting a lot of kinetic energy. That's it. In a third attempt, it's going to take us all the way up to here. The length of this is my kinetic energy added on my third attempt, shooting our projectile really fast from the surface of the planet. Well, now our total energy is up here. You know, it's positive. We haven't had that before, right? Before we always had less kinetic energy than the negative value of our potential energy. So the total was always negative. Now we made it up to here, and my total energy is going to be here. Now you can see that the story is different, because the object is rising, right? It's moving to the right on my graph, meaning it's moving away from the planet. Its potential energy goes up, but it still has kinetic energy left. Oh, this is where the other one turned around. We still have this much kinetic energy left. We keep going. And now because this graph only ever gets closer to 0, it never becomes positive, there's always going to be at least this amount of kinetic energy left over. And so we keep going and keep going. We never stop. We never come back down. And, you know, soon any changes in potential energy with respect to our Earth, our starting planet, is utterly minute, and I'm out in deep space. I'm not going to come back. Maybe I crash into something else that's out there. Right? Of course, in this graph, we ignore the existence of other celestial bodies. So, how fast do I have to go? Well, technically I could have gone a bit slower. I could have just barely need enough, so my total energy is right here. Right? As long as I'm just barely above 0, or really right at 0, total energy, that means I'll always have a tiny bit of energy left, and I won't turn around. Right? And this minimum velocity needed to make it, to never fall back down, is what we call the escape velocity. Let's write that down. The escape velocity is the minimum call it the launch speed needed to not fall back down ever. Right? Of course, we assume there's no atmosphere. We assume that our motion is not like propelled, right? We don't have a thrust. It's just the initial speed is all that we need. And I know it's called escape velocity and then the launch speed. Velocity is just a value. It's kind of a misnomer. It should be called the escape speed. But normally it's called the escape velocity. Right? And so let's calculate it. So we're going to say, well, I have that 1/2 mv escape squared. This is my initial kinetic energy. That better be enough to arrive at a total of at least 0. Right? So I want a total of 0. So that better be, let me write it down like this actually. Never mind. I'm going to add to this minus g m over r, where r, what is r? R is the radius of my planet. Could be the Earth. And m is of course the mass of my planet. Could have left myself more space there. Right? That better be 0. It could be greater than 0, But when it's exactly 0, we're just barely going fast enough, then that's when we talk about the escape velocity. And if you look at astronomical data for various planets, something you might well find included is the escape velocity starting on the surface. If you start higher up, you climb a mountain, or you start already in orbit, okay, story is a bit different. You need a lower escape velocity because you start with more potential. But that's not what we're talking about. You're starting on the surface. So let's simplify this. I can cancel out the m's, and I'm going to find that the may first rewrite like this. M is the mass of the object. Notice it's going to cancel out. So the escape velocity does not depend on what the object is that is doing the escaping. And I should pl for planet, right? Okay, this is going to cancel out. And I am left with, I take the 2 to the other side, take the square root. So we're going to get 2, this is the 2 going over the other side, g m planet divided by the radius of the planet. Right, so this would be my expression for the escape velocity. Okay, well, now we're just left to work it out, right? So for different planets, let's have a look. For Earth, if you plug in the values for Earth, I encourage you to do that, like 6 times 10 to the 24, you know the Earth's radius, 6,400 kilometers, make sure you convert to meters. G, you know the value of G. Doing all that, you're going to find it's something like 11 kilometers per second. Now you plug in the value, I think it's slightly more than 11, right? Approximately 11 kilometers per second, right? So you get it out, you get like 11,000 and something meters per second. This is for Earth. The planet is Earth, right? You're going to get 11. What about the moon? If you jump on the moon, moon is more realistic because there's no atmosphere, right? If anything went that fast on Earth, it would burn up right away because of the air drag. On the moon, I think it's something like 2.4 kilometers per second. Again, you want to calculate that, find the mass of the moon, go online or find it in your textbook, or some other reference, plug in the radius of the moon, the mass of the moon, work it out, and you find it's about 2.4 kilometers per second. Right, so it could be a very fast projectile. You might actually be able to make it go that fast. This is very unrealistic. And so for any planet, you could figure it out. Or for the surface of the sun, what does it take to escape? Probably very fast, and you probably die. But that's not the point. The principle is what matters here. 2 more things to say here. The first one is that if you start at infinity, right? Imagine this is the planet, and you start over here. Or in practice, you might just start really far away, not infinity, but really far. And there's nothing else in the vicinity, then if you stare, you let go of whatever you're holding on to, you're going to start falling very, 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 very slowly. And as you get closer, you're going to speed up more and more and more at a faster rate, and you're going to hit the planet. Well, you can easily calculate, easily confirm that your impact speed is going to be exactly the same as the escape velocity. Why? Because to get from here to here, you convert a certain amount of kinetic energy into a change in potential energy corresponding to that distance, that separation change. Well, if you start here and go here, the value, the magnitude of the potential energy change is exactly the same, except you're converting it back to kinetic energy. So falling back down from rest, from infinitely far away, you'd hit the planet with escape velocity. That's the first point I wanted to make. The second point I want to make about this, and this is a bit counterintuitive perhaps, imagine this is my planet. And imagine I'm right here, and I take some kind of projectile, and I want to make it escape. You're like, okay, I'll shoot it straight off away from the planet. That'll work. It'll also work if you point at some other angle, like this. Right? In this case, it would do something like this, because it gets attracted towards the Earth. It might do something like this and end up going this way. But it will get away just the same and end up at infinitely far away, just in a different direction. If I go like this, well, it'll go like this, and it keeps getting attracted, and so eventually, it might end up going this way, depending on your launch angle. So your launch angle is going to change where the object ends up, but it does not change whether or not it actually reaches infinity, assuming you don't just slam it into the planet. But then there are different forces acting, namely the normal forces and friction and whatnot, as the projectile slams into the planet at 11 kilometers per second. Right? But other than that, direction simply does not matter in terms of getting away in the end. Okay, now let's change gears a bit. Let's look at energy in the context of orbits. Let's imagine you're in a spacecraft right here, and you're going around Mars. Right, this is Mars. A big circle around Mars. I'm only going to consider circular orbits, much like we've done in the previous lectures. Although the conclusion that we're going to come to also applies to other orbits, to elliptical orbits. Right? But it's a bit harder to prove. We're just going to think about circular orbits. I want to find a relationship between the kinetic energy and the gravitational potential energy. Right? So here's what I know. I know that the force on this thing, because it's going in a circle, is going to be towards the center, and it's the gravitational attraction of Mars. So I can write down right away that G m, that's the planet, times the mass of the little thing, divided by r squared. It's squared because I'm talking about the force right now, the force of gravity. That's equal to mv squared over r. Right? This is it's a centripetal force. Well, the gravity acts as the centripetal force, right? Circular motion, we understand that very well. Okay, well, I can simplify this a little bit. I could cancel the m's. I'm not going to this time. I'm just going to cancel out this r with this one here. Right, so there's one r left over here, no r left over here. And now I'm just going to multiply both sides by a half. Actually, I don't even have to do that. Let's just look at the expressions I got. On the left-hand side, I have gmm over r, right? I cancel out the squared with this. This was an equation of forces, right? Gravitational force is the centripetal force. But now, having cancelled out the r, I see that this is just the gravitational potential energy. Well, it doesn't have the minus sign, so it's the magnitude. And what is this? mv squared. The r's cancelled out, remember? So that's twice a half mv squared, or twice the kinetic energy. I could put, I guess, this around it too, but kinetic energy is positive anyway. Interesting, right? If I wanted to include the signs, I could have written that minus the gravitational potential energy is twice the kinetic energy. Same thing, it's just, without the absolute values, I actually think about the signs. Notice it just followed from this. Circular motion implies this for the for Newtonian gravity. In fact, this result generalizes to other forces that have an 1 over r squared relation to separation, and one other famous one is just electrostatic attraction and repulsion. But even if there's another dependence on another power, like r to the 5, there's a similar thing you can derive. And these group of theorems, in our case, this special case here, it's called the virial theorem. And it does apply to elliptical orbits too. In the case of elliptical orbits, you'd have to talk about the average gravitational potential energy and average kinetic energy during the course of an orbit, because both of them would keep changing. But in our case, circular orbits, very simple. The derivation is very simple. Gravitational force is centripetal force, cancel 1r, and you got it right there. It just pops out. Interesting relationship. Doesn't matter how high up you are, doesn't matter what the mass is. This is the relationship that's going to hold. The last question I want to ask is, what about MGH? Right? We worked with it in the past, it worked great. So we were able to derive the notion of mg, the weight, and little g, from the force of Newtonian gravity. Well, can we do a similar thing with energy? The answer is, of course, yes, we can. Let's say we are some particular distance from the center of the planet. Maybe it's the planet's surface. Let's pretend this is right here. Let's stick with the Earth. This is the radius of the Earth. Right. Now, of course, that means the left-hand part of this graph doesn't really apply, but never mind that. Let's not worry about it. We're just going to worry about this point right here. Well, suppose I'm standing on Earth. I can figure out what's my potential energy, right? I'm just going to read it off. And it's some value. The value doesn't actually matter because only differences from that value matter in terms of predicting how fast something is going to go, for example. Let's imagine I go up a mountain. Then I let myself roll down the mountain. Well, how high is the mountain? The mountain might be a kilometer, couple of kilometers if it's a really high mountain, but you know, it's not going to take me out here. Like, this is 6,400 kilometers. So by going up a mountain, I'm going to go over here, and that's already an exaggerated distance. I'm going to go from here to here. So all the change in potential energy happens in this tiny little interval. Let's zoom in. Take this, we're going to zoom in. There we go. We're zooming in this little area here. That's the line. Right here, just copy this line bigger. And what you notice is that the line is practically flat. It's a straight line. Not horizontally flat, but straight line. No bumps, no curves. Now you say, but you just drew it that way. Not true, I didn't. Because you just look at it here, right? It doesn't change its slope much as you go from here to here. Notice that I'm actually just zooming in onto the tiny little bit here. So maybe just draw those lines, right? Right here and here. Between those lines, because they're so close together, the slope practically does not change at all. So the slope is constant. Within this tiny interval. Even though I've climbed a mountain maybe, or maybe I just climbed up a couple of stairs, then this would be even closer together. But over the course of this small change, the slope just doesn't change very much. So we're going to define this to be our 0 point because only differences matter, right? So we're going to call the 0. It doesn't matter ultimately, because we're only working with what's the difference between here and here. And then, well, how far is that? Well, slope is the, think of it as the rise over run, or just the derivative of this function, depending on how you want to think about it. So here I can say, let me write it down more technical way first. U, the potential energy at the surface of the planet, plus some tiny change. This width here is my delta r. I go from here to here, delta r. Small change in my separation from the center of the Earth is equal to my potential energy at the bottom of the mountain plus the slope times this, because it's effectively a straight line. Now I just have to find the slope. What is the slope? Well, the slope is du dr, by definition of slope. Or we can think of it as the rise of a run calculated this way. That'll work too, with some approximation. Right? So let's take the derivative, and well, that's actually just the force. I mean, we know what it is, right? This is going to be g m over r squared times delta r. But we know what this is. This is just g. So I get g times m times delta r. Well, delta r is really a height. Might call it h. Right? Those are the same. A change in separation going from the bottom of a mountain to the top of a mountain, change my distance from the center of the earth. That's to say the same as I've gained a certain amount of height. So I'm back at MGH, just derived from our beginning, our expression. Just kind of working backwards, really. Now I notice I've been a bit clumsy here. Of course, the delta r has to come from here. The slope itself is just this part here. So really looking at this as a whole. Now, of course, what about this one? Well, that's where I say we're going to call it a 0. We don't care about it. We only care about differences. And if I roll back down the hill, that amount is still there. So let's throw it out. We could have done this more formally. Essentially what you do is you do a so-called Taylor expansion around a particular point. Maybe just to first order, meaning that you get a linear function to approximate your actual function. But that's what we did, except we didn't use fancy terminology, such as Taylor expansion. If you haven't met Taylor expansions yet, you'll meet them in a future calculus course, and you'll probably also meet them in the follow-up courses to this one, if you're planning to go there. Alright, that's enough about energy, Newtonian gravity. There's of course lots more we could say, as always, but I think we will leave it there for right now. Thanks for watching.